Welcome to Calculus Volume 1. In this video, I'm going to talk about Section 2.1, a preview of calculus. Let's begin by overviewing the learning objectives for this session. To highlight, we're going to be talking about the tangent problem, one of the main motivating problems in Calculus 1. We'll also be talking about something called instantaneous velocity, as well as the area problem, which leads us into an overview of what we call integral calculus. I want you to be aware that this particular section of the textbook in question is a high overview of everything that's typically covered in a first semester calculus course. If you don't come out of this section understanding everything completely, that's 100% okay. That's what the entire semester is for. So let's go ahead and get started. The first thing we're going to talk about is the tangent problem and differential calculus. Rate of change is one of the most critical concepts that we will cover in calculus. Let's look at these two graphs. We have f of x is equal to negative 2x minus 3, g of x is equal to x over 2 plus 1, and h of x is equal to 2. In this case, we each have three different constant types of rates of change. In the first graph of f, we have a negative rate of change. In g, we have a positive rate of change. And in h, we have a constant rate of change. In calculus, at least in the beginning, this is what we're going to be studying, rates of change. And then we'll talk about how they connect to the real world. So compared to functions like f of x equals x squared, which grows at an increasing rate, these linear functions have constant rates of change. So how can we find out how x squared is changing compared to things like x cubed is changing, or trigonometric functions, which are oscillating? So how do we approximate rates of change? Well, let's first talk about something called the secant line. We can approximate the rate of change of a function f of x at a point a f of a on its graph by taking another point, x f of x, on the graph of f of x, drawing a line through the 2 points, and calculating the slope of the resulting line. Such a line is called a secant line. Figure 2.4 shows a secant line to a function f of x at a point a f of a. Let's look at it a little larger. You can see how the secant line passes through those 2 points. Another important concept about secant lines are their slopes. So the secant to the function f of x through the point a f of a and x f of x is the line passing through these points, and its slope is given by f of x minus f of a all over x minus a. The accuracy of approximating the rate of change of a function with a secant line depends on how close x gets to a. The secant lines themselves approach a line that is called the tangent line to the function. In this figure, you can see the secant line that we had from the previous figure, and then we have two other lines. The middle line here, halfway between the secant line and what now is being called the tangent line, shows that as x gets closer to a, it approaches that tangent line, and that allows us to approximate the slope of functions at given points. So before this, we really only had slope of lines, but now we can start talking about slope of functions. Let's do an example. Find slopes of secant lines. Estimate the slope of the tangent line, rate of change, to f of x equals x squared at x equals 1 by finding slopes of secant lines through 1, 1, and each of the following points on the graph of f of x equals x squared. 2, 4, and 3 halves, 9 fourths. So let's look at how we would solve this. For part A, to calculate the slope of the secant line, remember that's f of x minus f of a all over x minus a. That's the same thing as f of 2 minus f of 1 over 2 minus 1, which gives us 4 minus 1 all over 2 minus 1, which simplifies to 3. Let's do this same process with the point 3 halves, 9 fourths. Again, we have the secant slope is f of x minus f of a all over x minus a. Plugging in those values for 3/2 and 1, we end up with 9/4 minus 1 over 3/2 minus 1. And this simplifies to 5/2. So we went to 3 to 2/2. And if we wanted to get even closer, we would make the value even closer to 1/1. Now we've reached our first checkpoint. Anytime you reach a checkpoint in the textbook or in this video series, I highly advise you to stop, or in the case of this video, pause, and attempt the problem yourself. This is a self-assessment to see how well you actually understood the example or examples that was just done. So go ahead, pause the video. I'll wait. All right. Now that you've paused the video and hopefully attempted it for yourself, let's go through the solution to this particular problem. Again, we want to calculate the slope of the secant line. Just like we did previously, we're given the 0.54 and 25/16. So when we plug that information in, we end up getting 9/4. So if you got a secant line slope of 9/4, you're doing great. Let's talk about what's called average velocity, and we'll introduce something called instantaneous velocity. So let s of t be the position of an object moving along a coordinate axis at time t. The average velocity of the object over a time interval, say a to t, including a and t, where a is less than t, or if you reverse them, t needs to be less than a, is given by s of t minus s of a all over t minus a. If you look at this closely, you'll see it's just the slope of the secant line again, except this time we're talking about velocity and position. As t gets closer to a, the average velocity becomes closer to what's called the instantaneous velocity. This process of letting x or t approach a in any expression is called a limit and is the foundation concept that we need to study calculus. Let's look at example 2.2, finding average velocity. A rock is dropped from a height of 64 feet. It is determined that its given height in feet above ground t seconds later, for 0 is less than or equal to t is less than or equal to 2, is given by s of t equals negative 16 t squared plus 64. Find the average velocity of the rock over each of the given time intervals. Use this information to guess the instantaneous velocity of the rock at time t equals 0.5. So we will use these two time intervals in order to calculate this. Notice that they're very close to 0.5. So let's begin. For part A, to calculate the average velocity, we'll use the average velocity equation, but it's really just the secant line slope. So we plug in 0.5 and 0.49, and what we end up with is negative 15.84 feet per second. That tells us that the rock is falling. Let's do part B. Again, taking that secant slope formula and plugging in the values, what we end up getting is negative 16.16 feet per second. So if we were going to kind of guess what would be the instantaneous velocity, and ultimately we would want t to be exactly at a, but we can't do that because we would have a divide by zero error. So it looks like we're really close to 16. So a good guess of the instantaneous velocity would be negative 16 feet per second. Checkpoint 2.2. An object moves along a coordinate axis so that its position at time t is given by s of t equals t cubed. Estimate the instantaneous velocity at time t equals 2 by computing its average velocity over the time interval 2 to 2.001. So go ahead and stop the video and attempt this yourself. See if you can come up with the answer. All right, let's look at the solution to this particular problem. Again, using the average velocity formula, notice 2.001 is extremely close to 2. So we just plug in those points and we get about 12.006. So we would say that the instantaneous velocity is probably 12 units of measure divided by units of time. I think I made note of that. There really should be some units here. All right, so let's keep going. Let's talk about what's called the area problem and its connection to integral calculus. Many quantities in physics, for example, quantities of work, may be interpreted as the area under a curve. This leads us to ask this question: how can we find the area between the graph of a function and the x-axis over an interval? We do this by approximating the area by dividing up the interval a to b into smaller intervals in the shape of rectangles. So here we have an area under the curve from a to b. Here we've broken it up into rectangles because we can easily calculate the area of rectangles, length times width. So let's look at a quick example of how we would do this. Estimations using rectangles. Estimate the area between the x-axis and the graph of f of x equals x squared plus 1 over the interval 0 to 3 by using the three rectangles shown in figure 2.10. So we'll go ahead and we need to calculate the area of each of these rectangles. Each of them have length 1, or width 1. Their heights, however, are what changes based on the function's value. So for the first rectangle, we just have a little square, 1 times 1. For the second rectangle, it's 1 times 2, which would be 2. And for the third rectangle, it would be 1 times 5, which is 5. So we would add all these areas up, and we would have 8 square units of area. And that would be approximately the area under the curve, but that's an underestimation. Now let's try this one. Notice the rectangles are a little different, but it's the same idea. Now I do have to make a note that if you plug in 3, you actually get out 10. So this should go all the way up to 10. So I have made another graph. I'm going to put it side by side here to kind of correct that. That is a mistake in the textbook as it is currently published when I created this series. But that's okay. We'll just keep going from there. Same setup though for the solution. We have 3 rectangles, rectangle 1, rectangle 2, and rectangle 3, with areas 2, 5, and 10. Each of them have width 1, and so if we multiplied 1 by the heights, we would just do 10 plus 5 plus 2. So we would have 17 square units of area for these rectangles. And this would be an overestimation for the area. So what we're really looking for is a happy medium. So we know that the area has to be between 8 and 17 from the previous example we just did. So to summarize this section, what we really want to think about is calculus is the study of change. How are things changing? So we will study slopes of graphs and relate them to how things change in this course. We're also going to later in the course study what's called integral calculus, where we're really looking at areas under curves or areas under graphs. And an interesting historical fact is actually integrals were found first. When Isaac Newton and Gottfried Leibniz were discovering calculus, if you want to say, or inventing calculus, depending on your position on the matter, when they were coming up with these concepts and ideas for the first time, they were actually studying integrals first, and derivatives was a nice consequence. But when we teach it, we've actually flipped the book. So we're going to do limits and derivatives first, and then study integrals later.